All right, off we go. I have a chiral alcohol here, and I'm going to react it with PBr3 to the left. So what are we going to get there? We're going to get a bromine where the alcohol used to be, and the stereocenter will be flipped. So the H gets pushed out over here. And in this reaction with TSCl and pyridine, let's look at what happened to our carbon with the O in the mechanism we just did. Was there ever an attack on the carbon that has the O? No. Here's the carbon with the O. No. Here's the carbon with the O. Nothing's happening to that carbon with the O. And here's the thing that doesn't happen to the carbon with the O, an SN2. So nothing happens to the carbon with the O. The O remains intact. That's the molecule down there. There's its short form, OTS. And yeah, nothing happens to that carbon's oxygen or the stereocenter of the carbon. So keep the carbon as is. Keep the oxygen as is. Keep the H as is. It doesn't say anything about short forms here, but you know, on tests, if you've been studying exams, and there are always lots of them to study, you'll see I often ask students to draw the TS group. I think you will be asked to draw the TS group next week too. So there it is. And the way I ask that is just show all the pi bonds. So in the reaction to the left, the S became R. In the reaction to the right, the S stayed S. But both reactions converted an alcohol into a carbon with a leaving group. Carbon with a leaving group. Excellent leaving group, Br. Br minus is the conjugate base of HBr, strong acid. OTS minus is the conjugate base of HOTS. Makes OTS minus an excellent leaving group. So in both analyses, here and here, we have come full circle to chapter 9. RX, secondary, SN1 or 2, don't know. 2, new, cyanide, strong, SN2. So I got one thing saying SN2. 3, solve, DMF. Of course, you were reading about these on the weekend, right? Not losing anybody here, am I? Polar product solvents, SN2. You better give me an SN2 product for B and an SN2 product for D, and they will be different products, won't they? They will be different products, but they will be related. You're doing a backside attack SN2 on a R stereocenter, it will end up S. Here's your cyanide. If I ask you to show all the pi bonds, I want you to show me all the pi bonds. And the H got pushed back. So look at where you started and where you ended. You started way over here. The PBr3 reaction involves an SN2, and then another SN2 that we just analyzed got you back to your original stereocenter that used to be S, and it's S again because you did 2 backside attacks. Here, S stayed S, and you made it into an excellent leaving group. So the cyanide is going to end up on a dash. That pushed the H out. And stereocenter is now R. So, believe it or not, today's lecture is probably the most important lecture towards making you a useful synthetic organic chemist for a simple reason. So pretend either one of these is a potential drug, and we need to be able to make both enantiomers and then test to see which one's the more effective drug, right? We learned about that. And usually one drug, enantiomer, is more effective than the other. And then you need to realize that in nature, alcohols are very common. This one's not a very common one, but in nature, alcohols are common. Chiral alcohols are common, but often only one hand of the alcohol is available to us in nature. So only one of the hands, R or S or whatever, is available, is cheap. And the other one just doesn't exist. So you shouldn't use it to start your synthesis because your synthesis just got more expensive. So we now have the ability of starting with any alcohol and getting either an enantiomer product from it, just depending on the protocol we chose. This protocol involved 2 SN2 reactions, so we got back to S on our stereocenter. Creating the leaving group here did not change the stereocenter, it just made the O into a better leaving group. And then the O left because it got kicked off with the cyanide, strong nucleophile. So that's powerful stuff. And that brings to a conclusion those reactions. And then the rest of the day, we're going to talk about, so our last topic, it's not a tiny topic. The last topic for our test will be acid catalyzed dehydration of alcohols. So we're going to look at the scenarios where they're primary, tertiary, or vicinal diols. Vicinal diols. Vaguely remember those? I hope so. We learned how to make them in chapter 6. So we'll do these two here, and then we'll do a sample problem that's got both in the same problem. And then next segment, we will talk about my favorite dehydration, the pinnacle rearrangement dehydration. So what's going on in both of these? Whether it's primary or tertiary, they will not react until you make the OH into a better leaving group. One method of making them into a better leaving group is to put a proton on them. How do you do that? Well, you need a strong acid. Sulfuric acid is the most common strong acid, most common catalyst that we make more sulfuric acid catalyst than any other chemical on this planet. Okay. So protonation makes oxonium. If you're a tertiary oxonium, what's your fate? Tertiary with a good leaving group, it's excellent actually. It's going to become a carbocation. Tertiary carbocation, 1, E1. And this is the only time you're going to see E1 as the predominant product. There's no nucleophiles around other than sulfate ion, and it's a terrible nucleophile. It doesn't like attacking cations. It likes regenerating the catalyst so we can start this cycle again. So sulfate's grabbing a beta H. Do you remember what beta means? Well, alpha was the carbon with the leaving group. Beta is 1 away. So this molecule has a beta H on this carbon, or a beta H on this carbon, or a beta H down here. But considering those are both methyls on the same carbon, that makes them equivalent. So we only have to look at one. So grab the beta H. Sigma becomes pi. That's elimination. When you make a new pi bond, it's elimination. Have you burned that in your brain yet? Elimination means make pi bond. Now this one, you can't make a carbocation. You're not allowed. No carbocation. So what's the other fate? Well, an E2 that requires a lot more heat, because E1 from a tertiary cation is going to happen a lot faster than E2 from any species. Unimoleculars are generally faster than bimoleculars because you don't have to wait for molecules to meet here. The slow step is making the carbocation. Here, the slow step is the elimination step. And you need a whole ton of heat here. 170 degrees compared to 50. 50, that's a really hot day. That's it. So which of these is a lot faster? This one, tertiary carbon. Which of these two products is major? This one. It's got more hyperconjugation than this. It's got 3 carbons attached to the alkene. Here's the alkene. 1 carbon group, 2 carbon groups, 3 carbon groups. This alkene has only 1 carbon group, 2 carbon groups. And this one is very hard to make. It's only got 1 carbon group. There's another reason this is so slow. So let's do our own version of this. We got that. And then we've got over here. We got that. And over here we'll have this. We use HOSO3H and some heat. And let's just do two of the many possible products. One possible product here. And another possible product. Oops, I got a nice line down there now. Instead of putting the double bond out here, I could put it out here. And I like that one better than this one because the double bond has more substitution. There are other products possible. Could have done this double elimination that direction. Could have done this elimination that direction. I just didn't ask for it. So I want to see some things. We'll do it down here. Question 1, which alcohol do you want to eliminate first? Answer 1, the one that makes the cation faster. Tertiary. Show me you know that by starting the mechanism using the correct alcohol. Lone pair on the tertiary alcohol picks up a proton from sulfuric acid, generates this oxonium. What's a tertiary carbon with an excellent leaving group going to do? Make a cation. I know you want to say SN1. SN1's not even an option here. You don't have any nucleophiles. And we have a nice carbocation. Tertiary. I need 2 copies of it. Why do I need 2 copies of it? Well, I see the same carbon becoming an alkene in 2 directions. And you can't have a molecule do 2 different things ever. So don't try. How do you get from here to here? It's a good question. And how do you get from there to there? How does one do that? So pretend you had a brain fart and you forgot how to do this mechanism. Go back to your knowledge of stick figures. How many H's are on this carbon? There's one. How many H's are on the same carbon? There's none. What got removed? An H. What took the H? The conjugate base of your strong acid, which you made back in the first step when you protonated your alcohol. Conjugate base of this was made way back when. Remember, it's called acid catalyzed elimination, or acid catalyzed elimination of water is also known as acid catalyzed dehydration. You got to remove an H from a carbon that's one away from the alkene, from the cation. Call that beta. Alpha beta. This is an alpha position. There's one of the beta positions. There's another. It's just not a good looking beta. Wow, all of them gone, huh? This wasn't a very nice drawing of beta. I chose to do this beta. In my other molecule, same questions. How many H's on this carbon here? There's two bonds showing there's two H's. How many H's there? One. That's where you have to lose an H from this beta position. What's going to take the H? Same base. Need another copy of it. You can't have one base do two different things. Some of you have tried. Don't try it. Even good students sometimes they'll have an arrow going to this molecule and then the same lone pair going to another molecule. Are you trying to tell me it did both? Please don't try to tell me that. That's not what happens. All right. Sorry, my phone is ringing. And that gives us this pi. Just hope that's not too distracting for you. Next up, we have to do elimination to make these two pi bonds. So we're going to get good practice. And we need sulfuric acid again. I might be trying to get a little too sly. We'll see. Lone pair picks up a proton. Lone pair picks up a proton. Oxonium species, both locations. There we go. So we no longer have hydrogen sulfate. Oh, sorry, we've made hydrogen sulfate. We no longer have sulfuric acid is what I should have said. Where's that black H now? Oxonium. So we know if it was a tertiary oxonium, we wanted to do carbocation, SN or E1. If it's primary, we don't even have primary here, but in the example on the top of the page, you couldn't do the primary carbocation, so you had to do E2. Down here, you can do E1 or E2. I got the same thing. I'll do one example where it's E1 and the other with E2. How's that sound? Because it's secondary. They're competing with each other. Looks like I need the double bond to end up there in both. So here's the E1 version. Exactly the same as what we did above it. Got a carbocation right there. Double bond here. And I need to grab this H over here. And I'm going to make this product over here. How do I do that? I grab the H. What do I grab it with? Conjugate base, sulfuric acid. And in this one, I could have, what is my other product here? There, got that one. I'll do this one as an E, I gotta go to here. Okay, same guy. I'll do this one as an E2. Why? They're in competition. What's gonna grab that H? Right here. Conjugate base of sulfuric acid. So I got this one as an E2. Similar alcohol, E1 slow. E1, here's the fast step. Rate determining is making the cation. Fast is the elimination. Get your octets back. So that's a nice logical stopping point. And we're going to do dehydration of vicinal diols as our final topic for test 4 right after we come back.